Okay, hello everyone. So today is an interesting day because I'm missing the last block today. I'm missing F block to take my engineering class on a behind-the-scenes tour of the humanities building. So I kind of forgot that I'd be missing my physics class because I'm organizing all the logistics and everything. So I feel kind of bad about it. But oh my gosh. What I'm gonna do, this is like a terrible, I feel so bad, but it's the only thing I can think to do is, so I'm gonna record our class today, and then for F block, their class is gonna be to watch our class. So, I know, if I had planned ahead, I would have done like a worksheet or something, but so I kind of planned for today to be like, hey, listen, and learn, and whiteboard and everything, so, hello F block. I'm so sorry. It's gonna be fun. We're gonna try something new. So today, just a quick review of the schedule. Today we're gonna talk about the introduction to projectiles. So then on Friday we can do some projectiles practice, which will get us ready for our practicum, which for you guys is gonna be on Monday, and for FLF is gonna be on Tuesday. Then we're gonna have 2 days that are just dedicated to only review, no interruptions, no quizzes, tests, nothing, just review. And then your final exam, which again for you guys is going to be on Monday, and for F block and E block is going to be on Tuesday. After that, we're going to do a final project in the last 4 days of school, and it's going to be fun. And we'll talk more about that later. But make sure you come for the last day of school, where we're going to launch our final project. Yeah. So are there any questions about your final exam or your practicum the next 2 weeks? Yeah.
What units are on the final exam?
That's a great question. What units are on the final exam? So the final exam is going to cover 5 topics, and I keep saying these out loud, and I keep saying I'm going to give you a handout, but I just keep forgetting to make the handout. So I'm going to write the topics on the board. You may consider writing those topics in your lab notebook, because I've decided on the 5 topics. Topic number 1 is going to be forces. Actually, let me make that topic number 2 just so they go in order. Number 2 is going to be forces, which is unit 6. Unit 5. No, unit 6, I'm sorry, I'm a little flustered right now. We got forces, energy, which is unit 7. We got motion, which is unit 5. You guys with me? Motion, forces, energy, that's what we've learned this semester. And then the last 2 are stuff that we've learned all the way back starting in unit 1, and we've done in every unit since. So the last 2 are going to be experimental design, which I know we started learning in August, but I feel comfortable putting on the end of year exam because I feel like we've done it all year. And then graphical analysis.
What's experimental design?
So what it's going to be is, you know how like when we do an experiment and it says question, procedure, sketch, it's basically going to be that, but you're going to have to fill in everything on the page.
Like a lab setup?
Like basically a lab setup page. That's a good way to think about it. And it will be, I don't know that it's going to be exactly like one of the labs that we've done, because then you could just sort of copy it over, but it'll be kind of similar to something that we've done. So to here, this will be good to review all of the labs that we've done. And then here, graphical analysis, that'll be like, hey, here's a graph. What is the slope? What is the meaning of the slope? Hey, here's another graph. What is the area? What's the meaning of the area? Hey, here's another graph. What's the meaning of the vertical intercept? You guys, we've been doing that all year. Feel kind of comfortable with that? Yeah, great.
It's not going to be like a super long exam, like not like 100 questions.
So it is going to be 5 questions, and each question might have like 1 or 2 or maybe 3 parts. But it's going to be 6 pages. I've kind of already decided 1 page, 1 page, 1 page, 2 pages for the experimental design, just to give you space to spread out, and then 1 more page. So 6 pages total. And we're going to be doing it in the class block, so it's only going to take 1 hour on that Monday. We have 1 hour during the regular class block. And remember, it counts as the same way as a regular test. So regular time for the test, regular weight for the test. The only difference here is it covers more topics than just one topic at a time. Yes, sir.
Will we be allowed to use our lab notebooks?
Okay, this is a great question. You will 100% be allowed to use your notes. Now, I need to get a final answer on this. We're still deciding if your notes is your entire lab notebook or is going to be a condensed note packet that we're going to work on in class on the 12th and on the 14th. If it were to be a condensed note packet, what that would probably look like, just because, honestly, your lab notebooks at this point are 150, 180, 200 pages long, so it might just honestly be inconvenient for you to flip and try to find that one needle in a haystack. It might be better if we spend these 2 class periods condensing all that information into what I was thinking of. I was thinking about a little like 8-page note packet where you had a page for Unit 1, Unit 2, Unit 3, Unit 4, Unit 5, Unit 6, Unit 7, Unit 8. 1 page for each unit, and then we can spend this time kind of making our like cheat sheet study guide note packet thing. So it's either going to be your note packet with no lab notebook, your note packet and your lab notebook as kind of like a backup, or if we decide not to do the note packet, then your lab notebook. But in any case, you will have access to notes. It's just if you're going to have access to your whole lab notebook, and I want to have that answer for you guys by the end of the week. So we need to meet with the whole physics team needs to come together and decide. And Mr. Taylor's out today, and I think Mr. Stancy's out tomorrow. So we'll get the answer sometime. Yes.
Will the note packet thing, if you decide to do it, have like a list of all the equations?
You can put whatever you want in your note packet. So I would highly recommend in your note packet you write all the equations. Which I think would be a very good review activity for these 2 days for you to go through, and we could do it as a class. You could do it with your group. We could do it individually, but try to figure out what are all the equations that need to be in there. So, I like the idea. How do we feel about the idea?
I like it. Because if I'm trying to look for something in my lab notebook, like I have 2 lab notebooks.
Yeah, my other class said both. They liked both just so that they had like the backup plan of the lab notebook. So that's what I'm going to be advocating, unless you guys suggest otherwise. But we'll see. All the physics teachers kind of want to do the same thing. So we'll see kind of what we decide on. But if it is just the notes packet, then you guys are. I know you are going to put in your effort and make a really good, useful, helpful, perfect, awesome note packet. If that's the way that we go with it. So okay. So without further ado, let's get into projectiles. Today is a projectile introduction day. The reason that we're talking about projectiles is because projectiles are a really good way to review everything that we've done all year, specifically because projectiles involve motion, they involve force, they involve energy, and then experimental design, graphical analysis, that'll come in like when we talk about the practicum and everything. But so as far as reviewing these 3 things, these 3 topics all at once, the best idea to do that is projectiles. So does anybody know what a projectile is? Christian, what's a projectile?
It's like something flying in a speed in a certain direction.
Yeah, something flying at speed in a certain direction. So I have actually a couple examples of a few projectiles that I want to show you. So here's a projectile. Here's another projectile. They don't all have to be like, okay, projectile. Here's another projectile. Oh, that was sad. Okay, so those are all examples of projectiles. What kind of similarities do we notice between all those projectiles? They were all moving. I think that's a fair. I think all projectiles are moving at some point. Oh, hold on. I have another example of a projectile. Projectile. Well, not a projectile. Projectile. Not a projectile.
They have to be like in the air.
In the air. That's definitely true of all projectiles.
They have a force acting on them?
They do. They do all have forces acting, or a force acting on them. So actually, to kind of think about that, what I want you to do is, if you wouldn't mind, we're actually going to focus in our attention on this projectile. And what I want you to do is, on your whiteboards, This will be probably a quick one. What I want you to do is I want you to split it in half, and over here, we're going to focus on the forces. This is the forces. The forces happening during the launch, and then after it's launched, I want you to show me the forces during the flight. So the forces hold on. But before you move, just let me show you. I want you to show me the forces right here when I press, and then the forces as it's moving through the air after it's left the cannon. Does that make sense? Okay, I'll see how quickly we can do this. So F block, you guys can either sit there in awkward silence while everyone here does their whiteboards, or you can try to make the force diagrams on your whiteboards as well. Or I guess theoretically you could also fast forward in the video. That is definitely an option. But what I would recommend would be to get those force diagrams going on your whiteboards, because that'll help you kind of understand the conversation that we're about to have. So, again, apologies for this kind of weird way of doing class. But yeah, it's kind of what we're doing. So, thank you for your flexibility. One more time, we're drawing two force diagrams, one for the launch, one for the flight. Two force diagrams.
Well, at launch there would be spring force acting this way. And he means like right out
Yeah,
of the edge.
real short and extra long.
There we go. Stop.
Okay. So. There's a spring in there.
Take 60 more seconds, 60 more seconds.
No, we don't even have the flight.
Do the flight. It's easier anyway. It's just like in here. So we have first.
Wait, there's no F1. Because it's in the
Yeah,
air.
I know.
What's not going down?
There's not. When he shoots,
Oh,
there's
yeah.
not.
Pushing up on
So
it,
we
right?
have force. No, there's no force. Would drag force be negligible here?
Great question.
Maybe we just do like a T.
What?
Well, no, negligible drag force. Tiny, it's itty bitty drag force. Tiny itty bitty drag force.
Depends on which way it's moving. I think there's stuff in there. But this one's not the other one.
Because it makes a little sound when it implies that there's some force pushing through.
This was what you used, right?
Mm-hmm.
Okay, I just want to make sure, because you threw stuff.
Yeah. Okay, let us see what our force diagrams look like. We have a bunch of different force diagrams. It's very fun to see. The first thing I'm seeing on all these force diagrams is, let's see, so we have, so for the launch, we sort of need to remember how to do force diagrams, so this is a good little review. You can do a box or a dot, doesn't matter. So the force is on the ball. Who would like to take the lead for what forces are acting on the ball? Okay, Grace, take it away.
Force push to the right.
Okay, so we have a force push in this direction.
We just kind of said it was force push, but it's by air, right? Like is it a spring in there or air?
So it could either be the spring pushing on it or the air pressure pushing on
It
it.
doesn't matter.
Yeah, because different projectiles work different ways. Sometimes it's a person pushing it, sometimes it's a spring, sometimes it's air, sometimes it's like an explosion, like with a cannon or whatever. So we've got a force push. What else do you have?
We had force normal and force gravity as like.
Okay. Who agrees with this? Who thinks this is kind of pretty right? Sort of right? Nobody?
Nobody agrees with us?
I agree.
Oh, Will agrees. Wonderful. Giselle agrees. Marshall, I saw you didn't raise.
Move the laptop a little bit
Oh, yeah.
closer.
I'm sorry about that. Is that better? Okay. Marshall, I saw you didn't raise your hand. What do you have that's different?
So this might be wrong because we haven't done forces in a while.
Yes, this is a good review.
Wouldn't there be like one on the other side if it's not moving at the launch? But I don't know what that would be. Like,
Okay, so that's actually a great question. So you're probably doing it right here before I've launched, because right now, what can we say about the velocity of the ball? Zero. So therefore, is it changing or constant? Constant forces means?
Constant velocity.
Balanced force is constant velocity. That was my bad. But then as soon as I push, then what happens to the forces? Specifically, they become unbalanced, and we know that because unbalanced forces means a change in velocity. Exactly right. In what direction does the ball experience a change in velocity?
To the right.
To the right. Is it only to the right? And up. Does everyone see that? So that means that in the horizontal direction has to be unbalanced to the right. And the thing that's wrong about this force diagram is the forces also have to be unbalanced in the up direction. So what I would say is what I would actually have, I have this force push at an angle. Remember, we can't have force pushes we can't have forces at an angle. So I would say we have this force push. Maybe this force norm doesn't necessarily equal force gravity, because remember, force norm doesn't always equal force gravity. It only sometimes does. And so then if this were on a grid, we could go through and count. But what would we be looking for to make sure if this was on a grid was true? The forces have to be balanced or unbalanced? Unbalanced in both the horizontal and the vertical direction. So, Kira, can you talk to me, are the forces balanced or unbalanced in the horizontal direction?
Unbalanced.
Unbalanced, and why do you say so?
Because the diagonal arrow is a lot longer than the other two.
So we're looking at the horizontal direction. Which forces are acting in the horizontal direction? The horizontal also is code for left and right.
So there's no force in the, to the left.
So there's no force to the left, and what force is acting to the right? We remember a component of this force push is acting to the right. Let's just say 4 squares, I just made that up, but whatever. 4 squares to the right, 0 squares to the left. Is it balanced or unbalanced? Unbalanced. Okay. Shaw, can you do it in the vertical direction for me?
Do we know how many squares?
You just make it up.
Well, it's
Let's say gravity is 1, 2, 3 in the down direction.
Well, we know it's unbalanced because it's going up.
Okay.
The actual ball. So if F grav is 3, then you can say F norm is up 2 and F push is up 2.
Okay, so this is 1, 2, and this is another 1. I'm just going to do 1, 2, 3 just because I made it a little bit longer. So if we have 5 up and 3 down, then is it balanced or unbalanced? Which means what's going to happen with the velocity?
It's gonna change.
Change velocity to the right direction and to the up direction. It's going to accelerate to the right and to the up. We all okay with this? Okay, so now here's where things get really interesting. So Eric, what was your force diagram for when it was just in flight?
We had that there was force drag to the left and force gravity in the downward direction.
Okay, so and so we have a force drag. So the thing about projectiles, just to make these problems easier, the way that we're going to approach projectiles is we're going to say that force drag is negligible. It's so small that we can ignore it. Which in some situations, like, we don't usually treat feathers as projectiles. We don't usually treat really light things as projectiles. And so the reason that we do that is because if we ignore force drag, then what do you notice about the forces on a projectile? There's just force gravity, which is good. This is good. But you'll notice that, how is it true that a projectile is moving to the right if there's no force to the right?
Something did push on it to the right, and it's still moving to the right. There's just no force currently acting on it.
That's exactly right, and that's exactly what I want you to remember. In the air, there's only force gravity, but it's moving to the right because a force did push it to the right before the problem happened. A force did push it to the right, and then it maintains that velocity because of Newton's first law. Because balanced forces, you guys notice that in the horizontal direction the forces are balanced, right? What does balanced forces mean about velocity?
Constant velocity.
Balanced force is constant velocity, so it's going to maintain a constant velocity. Does that mean it has to maintain a constant velocity of 0? No. So if because of this force push, it got a horizontal velocity, Vx equal, I don't know, 5 meters per second, what's going to happen to that velocity in the x direction?
Still going at 5.
Still going at 5. It's balanced force is constant velocity. But what is happening to the velocity in the y direction?
It's not balanced.
Specifically, are the forces balanced or unbalanced? They are unbalanced. Unbalanced forces means what in terms of velocity? Changing velocity. And we actually know that the change in velocity, or the acceleration caused by gravity, the acceleration in the y direction caused by gravity equals the acceleration caused by gravity?
Change velocity.
Negative 10 meters per second each second, which Brendan said was a change in velocity. Specifically, how is the velocity changing, Brendan? Every second that goes by.
Velocity is
Mr.
getting
Boltri,
Hold on, let me.
would it be that the velocity is getting greater every second?
So every second that goes by, the velocity is changing by how much?
Negative 10 meters per second.
Negative 10 meters per second. Yeah, Sierra.
okay, you just cut out and now you're mute.
Oh, thank you so much. I did cut out, and I'm glad you're back. And now hopefully I'm unmuted. Thank you for letting me know. So we know that in the horizontal direction, and we have a constant velocity. In the vertical direction, what is happening to our velocity? Is changing. Are we all okay with that?
So
Kayla.
you can have, so you can be balanced horizontally but not vertically.
Exactly. So this is one of the things that I wanted to review. Is that in the horizontal direction, you can have a balanced force, which means that in the horizontal direction you have a constant velocity. In the vertical direction you can have an unbalanced force, which means that in the vertical direction you have a changing velocity.
So does that mean that while, like, is it just like falling in the air, like, or?
So this is a great question, and actually gets to basically the next thing that I want to talk about, which is let's look at what is if we were to make a graph of the velocity in the x direction with respect to time, and the velocity in the y direction with respect to time, what would those two graphs look like for the example shown of the projectile? the velocity in the x direction with respect to time, the velocity in the y direction with respect to time, and you'll notice that this is a review of Unit 5 motion. So just to practice that review, can everyone please take 3 minutes on your whiteboard and make the velocity in the x direction with respect to time and the velocity in the y direction with respect to time. Again, F block, thank you so much. You're paying such good attention. I know it's really hard to watch a class that you're not part of. But this can be your little break. You can have a little chat break. You can work on the graphs. As always, please feel free to email me if you have any questions.
I think we're just doing it over the course of the entire thing. Because it's going to the negative. So we go from 0 and then we go up and then we just stay out. Does that sound right?
Let's have time 0 be the moment that it leaves the cannon. The moment that it leaves the cannon is time 0.
That changes things.
It does.
Just like at the start of the interaction when it's chilling inside and not inside. So in that case, we just do like.
Yeah, is this right when it leaves cannon?
Right when it leaves the cannon, just till the point that maybe it hits the ground. But not including that.
See what I'm saying? That's why I was confused. You're saying the velocity
Oh,
is
there
higher.
would be no upward velocity in the.
Velocity is not
unless
higher.
the ground is down. Yes. Your rate is something.
Because it goes up and then it comes down, right?
It's going away.
Does the ball ever go up?
That's what I said. But the velocity's so, but it's not in the negative direction. So it's slow as a curve. I think it goes like this. I mean, no. It starts.
I love this as a review.
It goes up.
Such a good review.
I think it goes up. Well, it starts. It's not shared. Okay.
I love this as a review activity.
From the way it looks like you're showing it.
So we need the line.
Okay, let's bring it back to have a conversation. In the x direction, so I should have been more clear about this, but in the x direction, we're talking about the moment that it leaves the launcher. Because for projectiles, what we really want to do is we really want to focus our attention in on the flight. Whatever launch happened, and then what we really want to do is we want to focus our attention on the flight. The reason why we want to do that is because then the forces in the horizontal direction are balanced, vertical direction are unbalanced. If we try to look at this, things get really complicated. But don't worry, we can do this with energy, which we'll do that in a minute. But for right now, let's focus on the flight. So who can just talk to me about the initial velocity in the x direction and the initial velocity in the y direction when I launch it, which is right here? Who have I not heard from in a minute? Giselle. In the x direction, did it have a positive velocity, 0 velocity, or negative velocity? Positive. So just we can get ourselves started by adding a point right here. Which, for example, in terms of getting partial credit right away. And then Giselle, in the y direction, when it left the cannon, was it moving up, was it moving down, or was it moving completely horizontally? It was moving up, so what does that mean for our y velocity at the beginning? If we're moving up, is our velocity positive, 0, or negative? If we're moving up, we've defined up as positive, so that is a positive velocity. You guys with me? Okay, so if we can at least get started, then that'll help us get on the right track. Okay, Sierra, are you there?
Yes, I am.
Okay, Sierra, talk to me about what would the velocity look like as time goes on in the x direction?
It would get smaller.
So remember, talk to me about the forces in the x direction.
Okay, so they're balanced.
They're balanced. What does that mean for the velocity?
And it's constant.
Constant velocity. What does that look like on a VT graph?
I think it's a linear line.
Linear line specifically will help her out.
A straight, horizontal.
Horizontal line, because that means, let's say it's 5 meters per second. That just means it stays at 5 meters per second for the whole time. You guys with me? This is where we got the equation. You guys remember that the change in position equals Vx times delta t. How did we get that equation? Length times width, it's the displacement is the area of a VT graph. Okay. So then, Connor, would you mind talking us through what happens to the velocity in the y direction? So Giselle said that it leaves the launcher and it's moving up. Then what happens to it? So it keeps moving up for a little bit, right? And then it gets to the top, and then it goes down. So what does that look like on your graph? It goes from positive to at some point it needs to get itself to 0, and at some point it needs to get itself to negative. Does everyone agree with that? Does that kind of make sense?
Yeah.
So Haven, we said what was going to be the acceleration in the vertical direction based on gravity? Yeah, the up-down acceleration. Because the only force acting on it is gravity. And what does that acceleration do to gravity? Well, I'm out of frame. What was that?
Negative 10.
Negative 10 meters per second squared, or meters per second each second. And where do we see acceleration on the VT graph? It's the slope, because that means that every 1 second that goes by, the velocity goes down negative 10 meters per second each second. Does everyone see that? So these are what the two graphs would look like. We're okay? We'll notice that this, how many constant accelerations, is the acceleration constant here? How do we know? Yeah, we could find the slope of the line. The slope of this line never changes. The slope never changes, it's negative 10. If we have a single constant velocity, then what can we use? We can use our big four equations, which might be worth remembering. If you don't remember them, let's see, we got Vf equals Vi plus A delta t. We got the change of position equals we got the change of position equals the initial velocity times the change in t plus 1/2 A t squared, delta t squared. We got the change in position equals Vi plus Vf divided by 2 times the change in time. And we got Vf squared equals Vi squared plus 2A delta B. You guys remember these equations? You guys remember where they all came from? Where did this one come from? Just shout it out. Acceleration is the slope of a VT graph. Where did these two come from? It's the displacement is the area. This is the rectangle triangle method. This is the trapezoid method. And this one came from a variable substitution. Yes? Okay. Woo! So we've reviewed forces. We've reviewed motion a little bit. I know it was only like a 5-minute review. But now, just to give you kind of a sense of what we can do with a projectile problem, I want to do a projectile problem together as a class. Sean? Yeah, that's great. But what I was thinking was like, okay, we could start with like the easiest question and then work to a medium question and then work to a hard question. But we kind of don't have a lot of time. We have about 20 minutes left. So I thought, you know what? Let's just jump to the hardest question possible. Does that sound fun?
Yeah.
Yeah, because then we'll all do it together. And then what we're going to do on Friday is then I have a worksheet packet for you that starts with the easy questions, then works to the medium questions, then works to the hard questions. But what I thought today is let's just jump to the hard question and see how we can do. Because remember those videos that we've been watching about your brain? And sort of there are two different ways that you can respond to a hard question. You can just be like, oh, this is too hard, I don't want to do it. Or, alternatively, you can.
Not do it yet.
Yeah, maybe this is too hard to do right now, but we can continue to struggle, we can continue to try, and we can continue to get there. So let me show you the problem, and then I have a question for you. What pieces of information do you think that you need to know in order to be able to solve this problem? And then we'll talk about it as a class. But I'm going to show you, and I'm going to give you like 2 to 3 minutes as your teams to try to think about how you would solve the problem. You guys with me? Okay, I have a problem over here. Oh, uh-oh. Remote learners. Okay, so what I have, excuse me, sorry, coming through. What I have over here is I have a projectile launcher. So this projectile launcher, I have a little pump here. I can pump up the pressure. And as the pressure gets more and more, then I can load in one of these steel balls. I can load in a steel ball into the chamber. I can arm it, and then I can launch it. And it lets go a big puff of air, and then the projectile flies through the air. You guys with me? My goal for you today, and this is going to be similar to your practicum, is to place this Coke bottle where you think the ball is going to land such that we can hit the Coke bottle and send it flying. Is that kind of clear?
Yeah.
So we could send it right here. That would kind of be a little wimpy of a ballistic, or we could, I mean, if we got like a super extra mega strong, maybe it like goes all the way to over here. You guys with me?
Yeah.
So this problem is really good because it involves in the horizontal direction, the object moving with a constant velocity, because what are we really trying to solve for?
Change position.
We're trying to solve in the change of position in which direction? The change of position in the x, the change of position in the horizontal direction. We want to know from here, how far in the horizontal direction should I place my water bottle, right? Does that make sense to you?
Yeah.
But in order to know, in order to figure that out, what do we also have to think about? What's happening in the y direction?
Like gravity.
So we have to think about those two pieces of information. So what I want you to do is I want you to list out on your whiteboard, what are some things that you would like to know about this problem? What are some, because over here I've measured everything. And I can give you the measurements, but you have to ask for them first. So think about what measurements you want me to give you. The only thing I definitely won't give you is the change in distance in the x direction. Because that's the whole point of the problem.
Ow.
So hopefully this makes sense to you guys. And again, I'm sorry that you're not able to see it kind of in person, but we have our projectile launcher. We're trying to think about what we need to do in order to figure out the right place to put the Coke bottle. Yes?
Do you know what the VIs and VFs are?
Let's talk about it.
What else do we want on our list of demands?
List of demands.
That's all I can think of, because you just put it in the equation I was specifically looking at, the third equation. But you could really use any of them except for the first one.
Okay.
List of demands.
Okay, let's give everyone another 30 seconds. Or 60 seconds.
What about the mass of the ball? Do we need that?
You can measure that. There's like pressure gauges and that sort of stuff. But why would you be measuring around pressure? What would you be trying to solve?
Do we have our sauce?
So we would take that pressure and what number would you try to figure out based on that amount of pressure?
Okay, I think
So let's say it's 100 pounds, 100 psi. Actually, no, that is the pressure. What are you going to do with that number? 100 psi. say all those out loud. Those are really good. Uh-oh, I've lost my remote learners. Can you grab my laptop for me?
No, we only have acceleration for acceleration.
Sorry, remote learners. I know this is a weird day to miss.
We don't have acceleration.
Or not to miss.
We know it's a constant. F push. What push is that? Hide.
Okay, let's go around and hear what you guys are interested in knowing, starting with Christian.
So we wanted to know the mass, like how many times you pump up the machine, and how high the machine's actually off.
Okay, mass is 0.02 kilograms. The number of pumps, which gets to Giselle, what were you asking about?
Like how we could convert the pressure into something we could use in a fridge.
So the pressure equals 100 psi, which is pounds per square inch. And you said how high it is off the ground?
Like how high where it launches.
It launches from height of launch equals 1.06 meters. By the way, some of this is useful information and some of this is not, just so you know. Brandon, what did your team want to know?
We said the velocity final.
The velocity final, I'm just going to go ahead and say I do not know. I don't have any way of measuring that. If I had a way of measuring it, that'd be nice, but I don't. I do have a way of measuring the initial velocity. And I know the initial velocity to be 5.72 meters per second. It would be awesome to know the change in time. I left my timer at home, but this is a very important piece of information that we are going to need to figure out. We are able to calculate that though. I think we almost have enough information to go ahead and calculate that. There's one more piece of information that we know the acceleration in the horizontal direction is 0, and the acceleration in the vertical direction is -10, because that's just how projectiles work. So there's one more piece of information that you guys need to know, but you might not be thinking about it. But if you'll look over there at the projectile launcher, what do you notice about, what's going to be the direction of that initial velocity? It's going to be at an angle. So what more piece of information do you think you want to know? You want to know the angle. I'll tell you the angle is 30 degrees. What can we do with that information?
It is. Oh my God.
It's okay. I could have made it a 25, 65, 90, which,
It's useful. That's useful.
but then you guys know how to use sine, cosine, and tangent, so you could do it. Okay, but so this initial velocity, where do I put this initial velocity on the triangle?
It's on the hypotenuse.
It's on the hypotenuse because that is the initial velocity. So it's 5.72. So meters per second. So with that, what can we do with this piece of information? Math. Solve for. Can everyone please solve for me? What is the velocity in the x direction and the velocity in the y direction at the start?
It's VX. Sorry.
Yeah. Oh,
And then 2.86 root 3.
wouldn't this be 2.86 and this be 2.86 root 3 because this is the short leg and this is the long leg?
Oh, that's the, okay, yeah.
Cosine is opposite.
Sorry, I couldn't tell which one this is.
Cosine is opposite over hypotenuse. Sine is adjacent over hypotenuse.
You
No.
don't need cosine and tangent for this though.
Well, you don't if you have your 30, 60, 90 triangle rules memorized, which I do not.
Ah.
So yeah, this is 2.86 and this is.
Okay, Mr. Boltri. Do you want this written as the exact value or the
We can round it if you want to. 2 decimal places would be fine.
Because I think Dr. Aquino would throttle us if we rounded.
Unless she specifically told us.
Like no rounding pi and no rounding square root.
You can't round, you can't round cosine tangent. Are there other two?
I can round cosine tangent, usually.
Yeah, she usually has to do
It's
4.
the only thing we can round.
Yeah. But you can't round
But like,
square
if
root.
you round pi, you can die.
Let's take 20 more seconds.
Round pi and you die.
That's right.
Yeah, right. Like, look at the skills.
That's terrifying.
Skills.
Okay, bring it back, everybody. So this worked out very nicely because it was a 30, 60, 90, but I might give you other angles, so just remember, sine is going to be the opposite over the hypotenuse. Cosine is going to be the adjacent over the hypotenuse. So all you need to do is you need to do 5.72 times the sine of 30, and that gives you the velocity in the y direction. Or you can remember your 30, 60, 90 triangle rules. And Kaylin, what did you get as the velocity in the y direction?
I got 2.86.
Does everyone agree with her?
Yes.
2.86 meters per second. So this is, by the way, the initial velocity in the y direction, because we know what's going to happen to that velocity in like a second. It's going to go down. In the x direction, Marshall, what did you guys get? 4.95 meters per second, which, by the way, is this is moving close to like 10 miles an hour. So you don't want to get hit in the face by a 10-mile-an-hour little metal ball. So we're all going to make sure that we stand back when we actually launch it, which should be in approximately 10 minutes. So now that we have the velocity in the y direction, the velocity in the x direction, what can we do with these pieces of information? Well, if our goal, right, if our goal is to figure out how far it goes in the x direction, what's the last piece of information that I need to figure out how far it goes in the x direction? If I have the velocity in the x direction, all I need is delta t, and then I can find the area of this rectangle, because we know the area of a VT graph is the displacement, yes? So let me just make up a number. Let me say that it's in the air for, I don't know, 5 seconds. And let me just round this really quick to 5 meters per second. Then how far did it go? 25 meters. That's like most of the way to the humanities building. So it's not in the air for 5 seconds. But let's say it's in the air for, I don't know, 2 seconds. Then how far away do we need to place the water bottle? 10 meters. Okay, well that's into Miss Maney's room. So probably less than 2 seconds. But it's probably not good for us to just keep guessing as to how long it's in the air. Do we have any way of figuring out how long it's in the air for? Stopwatch, but that would require us launching it. Without launching it, is there any way to figure it out? An equation specifically, so that's in the x direction. If we solve for the delta t over here, if we solve for this delta t, what's the relationship between this delta t and this delta t? They're the same because it's in the air for the same amount of time in the vertical direction and the horizontal direction. The time doesn't care about the direction. So
we could do it with the horizontal one and do the first equation because we know that the df would be the same thing.
but that's not going to help us because these two are going to be, this is 0. So 0 times whatever time we make up isn't going to help us.
What if we made a graph for the velocity in the y direction and found the slope, and then maybe that would be
Okay, so yeah, so let's look at this velocity in the y direction graph. Are there any numbers that we can add to this? Oh, we know the slope. Slope equals negative 10 meters per second each second. We also know that, Grace, you said the starting value is 2.86 meters per second. And what is the change in position of the... Well, so if we have the initial launch height of 1.06, So what's the change in position? If it starts up here and then ends down here, the change in position is negative 1.06. So hold on, let's start to write out the information that we know. If we're looking for delta t, let's use the guess method. What are we given? We were given the initial velocity. This is all for the y direction. We're given the initial velocity, bless you, equals 2.86 meters per second. The acceleration equals negative 10 meters per second each second. And the change in position in the y direction equals negative 1.06 meters. And we're trying to solve for the change in time. What equation does that make us think of?
First one.
We don't have the final velocity, unfortunately. Second one. So we're going to write out our equation. Change in position equals VI delta t plus 1/2 a delta t squared. So we can solve for delta t. Then we're going to substitute and solve. Substitute negative 1.06 equals the VI 2.86 times delta t. Would you guys rather I write delta t as x just so we can solve it? Some people are more comfortable with that.
I kind of like it.
Okay. You kind of like, maybe we'll compromise, and I'll just write it as t instead of delta t. Okay, so t plus 1/2 times negative 10 is negative 5, so I'm just going to do minus 5t squared. Whoa.
That's a problem.
Shoot. How do we solve this? Who remembers? I think we learned this just barely in algebra, and we're going to learn it way more in algebra 2. So maybe Kaylin can come to the rescue unless anybody else remembers. Well, we don't want to square root it because then we're going to have the square root of t here also.
You're gonna have to put everything on one side.
So let's move everything to one side. So we get 5t squared minus 2.86t minus 1.06 equals 0. What can I do with this?
You have to do the big X with the.
Okay, so we could factor it, but the numbers here aren't really nicely factorable, unfortunately.
You do that weird equation.
Quadratic.
So what you could do is you could graph this. Do you guys know how to graph functions in your calculators? Okay, you're going to learn that next year. That's fine. But until then, does anyone remember x equals negative b plus or minus the square root of b squared minus 4ac all over 2a?
Quadratic formula.
Oh, wait.
Yeah, the quad. I know
See?
what.
The online part, like, no one even zoomed on online classes.
Oh, yeah.
In this weekend,
I like it.
Okay, well here's where it's useful, but hello, long story short, it's useful only in terms, this is how we solve, this is one way to solve a quadratic that we can't factor. The other easier way is just to graph it and look at where it goes through the zeros. But I'll show you the math on this just really quickly. This is just a formula that you have to memorize. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Which, negative, if this, so in this formula, this is a, b, and c. You guys with me? So what is negative b? 2.86. 2.86 plus or minus the square root of, what is 2.86 squared? Somebody help me out. 2.86 squared should be like close to 7 or 8.
8.1796.
8.18 minus, what is 4 times 5
20.
times 1.06? 21.2 divided by 2 times 5 is 10. What is 8.18 plus 21.2?
29.38.
29.38. What's the square root of 29.38? Should be like 5.3 or something. 5.42. 5.42. I'm going to eliminate the negative because that's going to give me a negative answer. What is 2.86 plus 5.42?
8.28.
8.28. What is 8.28 divided by 10? 0.828 seconds. So how long is the projectile in the air?
0.8.
0.828 seconds.
Yeah.
That was really, really hard. I told you guys, by the way, that we are starting with, this is the absolute hardest problem that I could ever give you. And what are we doing?
We solved
We're figuring it out. We're figuring out we are one step away from being done. We just solved for how long it's in the air. 0.828 seconds.
We plug it in.
Then we can plug this into our graph. 0.828 seconds times is not 5. We want to be accurate. 4.95 meters per second. We get, how far does it go? I don't think so.
If it's wrong, something like 0.4.
What is this times this?
4.
4 something? 4.1 meters. You guys want to try 4.1 meters? Let's do it. Okay, I'll put it just a tiny bit less, okay? Sorry, Giselle, may I move your stuff? Okay. Would anyone like to do the honors and place it at 4.1 meters? Come on. So this is 0. So that's 1, 2, 3, 4, 4.1. Just a little bit to the right. Okay, and actually, sorry, remote learners, I'm going to have to borrow you because I need to put you into this in order to make it work. It won't work unless it's hooked in. But I'll see if I can Pro. Okay. Giselle, can you actually just take one step to your left?
Wait, should we take the cap off the soda bottle?
Gotta wear eye protection. Let's see. So I gotta pump it up to 100 psi to make sure it's right. Okay. Press play. Gonna press. Gotta make sure they can see. So I'm gonna press arm and then launch. 3, 2, 1, launch. You guys cool? Yep. Okay. 3, 2, 1. And that was the bell. So.
Oh my God, that was perfect.
We're going to do some practice problems on Friday. Excellent job. By the way, this video will be posted if you want to go back and rewatch what we did. That was the hardest possible question, and you guys did a good job. Okay, thank you, remote learners. I know that was my F block. I know it was a really hard and long class to watch online, but you did it. You did a good job. I'll see you on Friday. Bye.